Hello, Mr. Spandan, can you hear us? Is it audible?
Can you hear me now?
Yeah, it is audible.
Yes, I can hear you all. Okay, let's see. If you have the slides, then maybe you can do a test run to see if the first slide is visible, or I can try from here.
Yeah, we are just sharing the screen. Let's check and confirm. PPT. Is it visible to you, sir?
Yes, it is visible. Can we start the slideshow just for once to see if I
Yeah.
can?
Is it okay?
Yes, I think this looks fine. Yep.
Okay.
Ritesh sir. Ritesh sir.
Yeah, yes, sir.
Yeah.
Good morning, Father.
Good morning, ma'am.
Good morning.
जब ये होगा ना मतलब हमारा स्क्रीन जब शेयर करेंगे कुछ नहीं आएगा। अभी आपको दिखाएगा लेकिन स्क्रीन पर जब होगा कुछ नहीं दिखाएगा। बस शुरू कर देते हैं। So let us start today's webinar. Namaskar, I am Dr. Ritesh Das, Associate Professor and Head Department of Electrical Engineering, Christian College of Engineering and Technology, Bhilai, and with me, my co-host, Mr. Sridhar Burla sir and Mr. Munna Bursal sir. A very good morning to one and all present on this webinar. Respected Reverend Father George C. Varugis, the Executive Vice Chairman of CCT Bhilai, Principal Madam Dr. Mrs. Dipali Soren, HODs of various departments, professors, research scholars, IT consultant Mr. Siri Varghese sir, and my dear friends, a warm welcome to this webinar on a beginner's guide to data analysis. It is an honor and privilege to welcome Mr. Spandan Das as our today's speaker. As an eminent scholar, Mr. Spandan was graduated from Indian Institute of Science Center, Bangalore, in the field of BSc Research in the field of Physics and Master of Science in Astronomy from Leiden University, the Netherlands. Mr. Das has a vast experience in the field of data analysis. I welcome you, sir. Now I am requesting our Honorable Executive Vice Chairman, sir, Reverend Father C. Varugis, to kindly bless the webinar. Sir.
Good morning to all, respected Principal Madam, our elevated guest, Mr. Spandan Das, HOD,
Yes, sorry.
Mr. Ritesh Das, other faculty members, and the technical team behind and with him, the other joined guests. Welcome to this session of Data Analysis webinar. Since time immemorial, data analysis is part of human life, part and parcel of human life. We can see that years back, our grandparents and their grandparents also, since ancestors, they used to analyze their performance. They used to analyze and they used to note down their expenses, their income, their belongings, everything. And analysis was done, but not in scientific way. Raw analysis was done which later on took a scientific pattern, and a new face was given. And now time has come over where data analysis is read out scientifically, where textual data analysis is done, and then numerical data analysis is done. The analysis is done as part where you can develop and you can get more results, which much more growth for yourself and for your business or for your household. Time immemorial, mothers, they have done their analysis in kitchen income and expense. It's very raw, but whoever does that, they control the entire event. Even if it is a kitchen, it is the income of a family. If the father, his income is X rupees, and he analyzes his expenses, so he can match how much he's earning and how much he's spending. It's a very simple thing, but very easily he can curtail his. He can come to a conclusion where he should curtail his expenses and where he can stride on his growth. So that is one better part of data analysis. Today's session, where we have that the data analysis for beginners or for beginning note data analysis. That is one part of a person, of a student to develop, but at the same time, when it's scientifically done, we have much better opportunity to grow ourselves in any field. It is now very important. So I thank Mr. Ritesh Das, who has come up with such a good topic, and also I sincerely thank Principal Madam, who has given consent, and the team behind, and our eminent speaker Sandan Das, who kindly consented to be present with his vast experience on scientific analysis on these parts, which is now an emerging science. It is our honor to be together, even though it's lockdown period, but virtually we are together as a one family around the table, sitting and discussing very big event, but on a small platform. May God grant you all the wisdom to guide the new generation in a much better way, where we can analyze very small data and come out with very good results, which is useful for the entire humankind. I once again thank and wish you all the best. Thank you.
Thank
I think essentially we now live in a world we actually hardly understand in some ways, but it also gives us a lot of ways in order to make our lives better. So with that said, I'll now go directly into my presentation, and I'll start off from there. I'll just ask one question before that. Should I turn off my video camera, or should that be fine in general? And everybody can see it probably.
Sir, it is better, sir. You mute your web camera also,
sure,
for better
okay.
clarity in the streaming.
Okay, I'm doing that right now. Please let me know. Is my voice now better?
Yes, sir. It is better, sir. It is better.
Okay, thank you very much. Okay, let's just start off. Well, as my title slide shows, this is going to be an intro lecture. What an intro lecture essentially means is that I'm now going to develop an intuition rather than giving you stuff to derive or to work out or something. It's more, so I would request all of you to relax, look at all the examples that we are going to have now, and then try to connect them with how we see the world in general. I promise you that I'm not going to use any equations. That's one of the first things that I started off with, essentially, because sometimes equations generally muddle the way in which people generally learn about something. So to start off, if we can go to the next slide. Okay, good, thank you. This slide essentially encapsulates my thoughts in general of what a lot of people have to go through at the moment. Data analysis has become such a buzzword that essentially there are just a lot of people doing data analysis at this moment. And essentially, it's a part of data science essentially, So data science jobs, however, are not really keeping pace with the number of people actually trying to do data analysis in that sense. So this is a very humorous interpretation of the label at which we are at the moment. So a person who is already applying should know at some level that he is probably not going to be selected, and yet even with that hopelessness we still apply, and because we actually love this kind of thing. Leaving that apart, let's now move to the next slide in general. Okay, to start off from the beginning, what event are we analyzing? Like, what event is data? For us, for our human body, we perceive the world around us basically through our senses. It can be through our eyes, through our ears, through our nose, through our mouth, through the sensation of feeling, and so on. So what all this means is that we interact with our environment, with our sense organs, and we take in the data that all these things essentially give it to us. Where is all this data processed? Essentially is in the brain. Now, this brain essentially takes in all this data, makes a whole environment, makes a model of the world we live in, and then tries to make sense of the world around us in general. But however, there are certain things in this world or even in the universe we just can't visualize or hear or touch or feel or something. One example that I can give is essentially the light from the sun. We only see part of the spectrum which is in the visible range. However, the solar spectrum, as we know, actually extends far beyond that, beyond in the ultraviolet, in the mid-infrared, in the infrared, in the submillimeter, and so on. A lot of this data essentially is not available to us because we are humans and we just don't have the sense organs to actually take in such data. So what do? We actually build instruments to take in the data and to provide it in a form that makes it accessible to us. Now, this accessibility is hugely important, which is why when I write that data is factual information in a desired form, it means that this desired form is in a way where we can understand it. So with that said, this data can actually be of various types. It can be natural, from the natural environment. It can be meteorological, making sense of the climate, of the weather around us. It can be financial, depending on the economic situation we are in, how the markets go up and so go down, and so on. Scientific, as we all know, we are basically doing all science, so we deal with a lot of data. Cultural, from the books we read, and so on. And well, this list just goes on. So now, with that said, now we just move to the next slide. Yes. So this is the thing that I have to indicate at the beginning in a very general sense, is that data by itself is not an indicator of reality. Essentially, because we are hamstrung in a lot of ways, the data we pick up does not essentially show all of the information of the object that we are trying to analyze. So we already know a very common example of various blind scientists or blindfolded scientists trying to examine an elephant and all coming to different conclusions based on which body part they interact with. Now here, this presents us a very good example of data collection in general. What all the scientists are doing is in general collecting data. They are collecting data of each body part at various positions in the XYZ plane. So this data collection essentially can be modeled in the next slide. Can you move to the next slide, please? Yeah. So I have just labeled all the scientists picking up the data that they want from the elephant. However, when I see it as an outside perspective, I see this as a random jumble of data, right? So just from seeing this, I will not know that this data comes from an elephant in general. If I don't know anything about an elephant, this is a very big caveat I have to say. If I don't know anything about an elephant, then this does not say me a lot about an elephant, which means I now have to bring this data together in a form which will make sense to me, which essentially is what data reduction is. If you move to the next slide. Yes, thank you very much. We now assemble all the data elements in the XYZ plane. We assemble this in a way such that all this data come from the positions they were in, all this data come from the same time they were in, all this data come from the same location they were in. Eventually, even if we have done it, our data collection is not complete, since this, as we can already see from here clearly, we have very limited means of collecting data. Often it's very difficult to collect all the data that is available, so we can only sample some specific location-wise data. So my question would be, and this is the intuition that we develop, how do we get the elephant out of this data in general? Let's move to the next slide. Yes. So as a title, in general, I want to ask, how do we as humans know that it's an elephant? Essentially, our brain cheats a bit. It already, what we do is that when we grow up, we already know from a lot of books or from interactions with people around us that the elephant as an animal has certain specific characteristics. So when we compare these characteristics that we already have in our mind with the characteristics that we observe, then it becomes very easy for us to actually know that all these things, the data that we are seeing, is actually from an elephant. So we are comparing a model of the elephant that we have in our brain with the hypothetical location-wise data that we actually obtain, and then we compare it. This gives an example of how actually we can start doing this for specific analysis in general, even if we are actually doing it for a machine. Which brings to the point of my next slide, which is the changing paradigm. Thank you. The thing is, we actually, for a long time in human history, we as humans essentially interacted with the environment on our own. Since the Industrial Revolution and the invention of the computer, in general, this has changed a bit. Since we now have the ability to process a lot of data that would not really be possible to reduce alone, we are now able to do it all through the means of computer. However, this presents a new challenge. How do we make a computer equivalent to a human? We can do this data analysis fine. We know science. We know how to do this. How do we make a computer do that? Like, how do we make a computer think? Now, this essentially delves into a thing which we call artificial intelligence that has a really wide history. It started off, the term itself originates from the 1950s, and since then has just blasted off into a lot of avenues in general. However, one specific aspect of artificial intelligence is machine learning, where we actually train machines to understand how to analyze data. I'm going to be a bit more specific about this point. In general, is that machine learning in data analysis is very important. However, machine learning is not necessarily data analysis. That's why this is something which I will not be going to describe more in this webinar. But I hope that this is a topic that will be delved in deeper in subsequent lectures. If we now move to the next slide. Can you hear me? Next slide. Okay, thank you very much. Yes. So with that said, now let's come back to the topic at point of data analysis. As we have already heard from Principal Ma'am, the data analysis is a process of cleaning, transforming, and modeling data in order to find something useful in general. But I have to put out a caveat that all this thing comes after you have inspected it. Inspection is really a hugely important process involving data analysis, where you just first look at the data. You just try to get a feel of it, and then try to develop intuition of how to actually go about the process of cleaning in general. I have now actually described what all these three terms are. Cleaning essentially is a process of removing corrupted or bad data. In general, a lot of processes in nature are stochastic, and so the data that we collect are not all useful or all necessary. In that sense, we can actually remove some of this data without actually making our future conclusions any worse. With that said, it is very important to note that even before removing this data, we have to justify why we are removing this data. which is a very difficult task, but it's something that is done regularly in general. Transforming data is a method of making it suitable for and quicker and easier analysis. In general, a lot of data can be analyzed in a lot of different ways. However, we don't necessarily have all the time with us. We have to make sure that we actually inspect and analyze the data very quickly, whether we are doing some project or whether we are building something, which means that we only have a specific time frame, which means that we now have to transform the data that we already have in a form which now makes it something useful for us, because we can now analyze it very quickly. This has various applications in science fields. In scientific field, where if I give an example, there's a huge multi-country collaborative telescope known as ALMA. It's in Chile. What it does is that it just captures data in the sub-millimeter range and then converts it into a set of pre-processed data that is stored in hard drives. Now, all this pre-processed data essentially cannot be analyzed by humans. So what we do is that we take all these hard drives and then we transfer them to the observatory that we actually work in. We use this data, we transform it into a form where we can work with, which then brings out the size of this data to a very reduced size, and then we analyze it to find scientific results. Modeling data is in general something which means that we have a set of data and we want to find a trend in that. This trend will allow us to actually predict something that is necessary for the future. This is very useful for scientific collaborations and business initiatives, where we have to understand how the market goes up and down, whether there is an imminent crash coming up, or, well, we have to justify some hypothesis that we have been looking for some time. In that case, all these three things allow us to derive something useful in general. Can we move to the next slide? Is there any question? Maybe I can see. Okay, no questions at this moment. Thank you. Okay, so now that we know what data analysis is, we categorize data analysis broadly into 3 different categories. It's not necessary that all these categories are independent of their own. Mostly when we analyze data, essentially we all actually do a mixture of all these 3 analyses. But in general, these 3 things differ in a lot of ways that we can actually make them all separate categories. The first is descriptive statistics, which essentially deals with the statistical nature of the data, which means that we now have the data. We want to understand what just describes the data in the minimal amount of statistics required. We will look at this. We will look at all 3 of this in more detail as we go on. So I'm just introducing the nature of data analysis here. So exploratory data analysis, as its name suggests, is essentially extracting trends in the data or patterns. So this can be from a huge amount of data, from a less amount of data, and there are various methods of doing this. Confirmatory data analysis, as its name again suggests, is using data to confirm something, confirm a hypothesis that we already have. Essentially, exploratory and confirmatory data analysis sometimes go very hand in hand. So there's not much to differentiate them when we are doing all 3 of them at the same time. Can we move to the next slide? Yes, thank you. Now, let's look at all 3 of them in detail. I'll go through all of them one by one. As I said before, descriptive statistics is just simple statistical stuff about the data that we have. It shows the very important things, and the very simple things that we generally use for doing that are the mean, the median, the mode, the standard deviation, skewness, etc. that we already probably know from our 10th and 10 to 12 schooling period in general. In general, the population census for any country is a very nice example where we actually use the statistics very easily. Because there's just a lot of data, we can compare different statistics based on the mean of this data, the median of this data, and so on. We can also compare between data sets, as we now see in the next slide. Yes, thank you. And I hope this, yes, the animation is loading. What this is this is a demographic growth comparison between two countries, between India and China. This is just based on data that we have already, based on different age groups and based on different years. Now, all the mean, median, and essentially the percentile-wise distribution of the population is very easily seen. What's also is seen is that all these two demographic trends also differ a lot. One of them clearly shows the outcome of the one-child policy that China had, whereas the one with India all shows a base that is actually still expanding, which means that our birth rate is still high. This is not the case with China. If we can actually also extrapolate this to see how this population will change in the future. And with this, we can actually already see that sometime in the mid-2020s, India is going to overtake China, just from this data alone. We just don't need to do anything else. If you move to the next slide, we don't always need an animated graph to show these things. Now, this is between Japan and US in general. Japan, as this demographic trend shows, has a declining population throughout the years in the young age category, because this shows the effect of a drastically lower birth rate and a high death rate, because now old people are living longer, but more younger people are not being born, which means that the demographic trend is narrowing. This is actually also the case with a lot of developed countries, where the death rate is reducing and the birth rate is increasing in general. With US, it shows a very curious trend where the death rate is reducing, people are living longer, but the birth rate is almost staying constant. This is, of course, a very curious case, but much of this is actually attributed to the increased immigration into the country. US has a lot of immigrants, and all of this actually makes sure that the trend at the young age and the working age stay wide. Can we move to the next slide? Yes, we can, as I said, we can also compare between a lot of different data sets. If we have different samples, we have the same samples of data. So as it has been done in this data set, we actually are comparing the demographics with the demographics of the people in the parliament in general, which shows that young India actually has a lot of old leaders. This is actually not really just the case for India. This is actually the case for a lot of countries in Asia. So we can just compare, and we can show, okay, this might show that there is a very diverse, there is a very different age group of people who are actually concerned about a very different age group of people. Whether it shows concern or not is not my point to say. It just shows a data analysis. Can we move to the next slide now? Thank you. Now we come to the topic, which is actually of vast interest for all of us. This is a thing that has grown in, that has exploded since the 1960s a lot, and essentially makes much of the data analysis that we do at this moment. This is known as exploratory data analysis. It was spearheaded by John W. Tukey. He is one of the most prominent data analysts from the 1970s, and I have just presented a simple outline of what actually happens in general. Generally, what you do is that you formulate a hypothesis, you collect data in order to validate the hypothesis, and then draw an inference. However, the thing is that oftentimes the data that we collect is very large, which means that not only can we just talk about the hypothesis one that we were talking about, using the data, we can actually formulate a lot of different hypotheses from actually just inspecting the data or finding patterns in that. This is essentially what exploratory data analysis is at heart. We just have a lot of data in our hand, and now we are just using it in order to find patterns, so that we can now look for other hypotheses and to validate it in general. However, I must make it a point. This is a point worth remembering, is that when we get a hypothesis from some data, we don't test our hypothesis on the same data. That's known as data dredging. It will bias our results to having the same outcome. So we just use another set of data to actually validate that hypothesis in general. Can you move to the next slide? Yes. Now, exploratory data analysis in general has largely been replaced by the word called data mining today. But there's a very simple thing why this has been done. Essentially, data mining, as its name suggests, is we have just a whole huge set of data, and we will essentially go like a miner. We'll just go and look at some of the patterns in that, some of the outliers in that, some of the very important specific trends in that, and then try to formulate some hypothesis. Like a very good example of this is essentially as we all use Google or Android devices, or essentially just use the Google search. Google has a lot of data about us. It does not essentially start off trying to get this data, but this data is very useful to us as it now allows it to formulate a whole lot of different things, which we will actually see in the next slide. But for this slide, we actually know that when we are shopping in some e-commerce site, we already can see something. If you buy something, there is already a section which shows that, okay, this is a thing that is recommended for you. How does the site know that this is the thing that is recommended for us? Essentially, it tracks us. It tracks what we buy. It also tracks multiple users throughout its whole platform, and it finds the patterns of how many people buy something and then buy this thing. If this is significant, and then shows you that, okay, this thing is recommended, please look at it. If you give it a negative feedback, then it knows that, okay, for some people it doesn't work, so maybe it will have to reformulate its algorithms. However, if it does significant profit for it, that means it is actually working, which brings me to the heart of the next slide. Again, throughout the internet, wherever we go, we are recommended stuff everywhere. In general, we'll speak about something. We will search for shoes at one point of time, and then we will be advertised a brand of shoes that we have been thinking of. We would have been thinking of buying a smart TV or a router at some point of time, and then suddenly an ad comes up showing a very specific, reasonably priced product. When we look at vacation centers, and then suddenly we are all shown all these options on the site, then what actually is happening? Most of this data essentially comes from Google AdSense. Then how does Google know what we are trying to look for in general? This brings me to the next slide in general. Yes, thank you. What Google does in general is that it has a whole suite of apps that it uses for computer, for laptops, for iPads, etc. So everything in this collects data about you. It collects data from this. It essentially finds patterns from your emails. It finds patterns from the documents that you have. It finds patterns from the video calls you do. It finds patterns from the news that you read. Not only that, it also passively collects your location data. It collects the users near you. If they have a Google account, it will also collect their data. It will also collect voice samples that you are speaking to it. If you say, "Hi Alexa," or "Hi Google, do this," that sample is stored in general to train it. So using all this, what it does is that it creates a user profile in general, tailored made for you. It knows about you, it knows your name, it knows about your relationship history, it knows what you spend on, or what you want to spend on, or what you even dream to spend on. It knows about your salary because it has your employment details. It knows about your location, which means that it can now sense what shop would be best for you. It also knows about your interests, which means that it can tailor make your recommendations based on that. Based on the feedback on this, it will continuously change this user profile, which is why it's dynamic. And then use this to recommend you stuff. Now, this pattern finding from all this vast amount of data that it collects is essentially what's explorative data analysis, or just data mining. How do we do that? Let's find out from the next set of slides. Yes, thank you. So essentially how data mining works, it basically works in two broad different ways, which is supervised and unsupervised. These both essentially are also types of machine learning, which I hope you will encounter somewhere later rather than I just pointed out here because they are the machine learning part. Now, this supervised machine learning can be ways of classifying the data, or finding trends in the data using regression. The classification essentially is one of the widely used techniques at this moment. It uses neural networks, it uses Bayesian networks, decision trees, and so on. The unsupervised learning, which is more prone to errors, but is equally important, essentially has two different types, association and clustering. Clustering in general is very important today, as we will find out later. Can we move to the next slide? Thank you. Here I've just provided examples of some of these techniques. Now, what happens in an association is that, let's see, this is the data of 8 different people shopping for something on an e-commerce website. So let's say the first person buys bread, peanuts, milk, fruit, and jam, and so on. The 8 people buy something according to their taste. Now, from this data, we can find some associative example is that if a person buys bread, there is a very increased chance of that person also buying milk. If that person buys soda, there is a very increased chance of that person buying chips in general, which also happens in a lot of fast food restaurants. If the person is buying bread, then of course, in general, there's a very high probability of the person buying jam. So these are all the associations that machine learning can help us make. Now, this association will make the e-commerce site tailor make the site more for your use. So when you're buying something, immediately the next thing in the associative net will be recommended to you, so that you won't have to search for a thing. You will be pleased with the site, you will buy from it more, and due to the increased user interaction, the site will grow. This is how Amazon and Flipkart essentially work in general. There's also another method of doing it, is known as classification. This is a method of actually classifying the users an e-commerce network has in general. So from the whole user database, it finds the data based on of how to differentiate the users that it has. Some of the users buy only the very lower price stuff. Some of the users are not prone to spending a lot. So it categorizes them into different categories. Also, based on these categories, from the spending habits themselves, it will know whether you have a lot of family members, and maybe you are using all of this to spend something, spend more or spend less based on one family member or not. This is a classifying network, and if you fall in one of these categories, you will be the site will tailor make their experience to make it easier for you to shop. Can you move to the next slide, please? Thank you. And as I said, this is one of the clustering is one of the most widely used ways for unsupervised learning in general. What we see on the left is a set of data in general. We just don't know anything about this data. Let's assume we just collected it by looking at some specific noise level at some point, or by asking responses from certain people and so on. However, what we want to see is that, do this data fall in some associations or fall in some clumps, which will make it easier for us to individually analyze all these clumps. So we can actually model a machine to actually make these clumps with us. Well, this example that we are showing is actually the example for K-means data analysis form, where you just give the value of K. Here it's 3, and then the data, and then the machine actually inspects the data, and then find 3 different clusters. These clusters are more similar to each other rather than the data in other clusters. It also makes it easier to find outliers. As we can see, some of these data points do not actually fall near one of these clusters in general, which makes it easier to see, okay, what do these outliers actually indicate? Are these outliers significant? Are these outliers not significant? And we can just put away all this data and so on. So if you move to the next slide. Yes, another example is regression. As we looked at it, we'll have a set of data points. We just need to find a trend on how this data essentially varies, so that we can actually make sure that you can use this model to essentially predict how a user might spend or might think of next. However, this essentially is a very sensitive thing to do, because we can sometimes overfit our data or we can underfit it. The linear regression in this part is an example of an underfitting. The multiple polynomial relationship, as we see here, has a high variance. It will completely fit all the data points, but it's pretty much useless in predicting anything because it has a very high variance. However, the one in the middle has a very correct fit, it has a low error, it has low bias, and it has low variance. That means this technique actually has a lot of different things that we can make it that we can use it to model or to use it to predict different behavior. And now we can move to the next slide. I just want to show an example of how clustering works. So this is a very simple example. Generally, countries based on different trends on the GDP, spending on their primary education, and so on, and expected life of living fall in clusters. Now, based on thresholds that we choose, we can actually find these clusters and put it across in the on a world map and say that, okay, some of these clusters do in fact make it divide it neatly into developed, developing, and underdeveloped countries. Now, I don't want to say that all of this data is accurate. In fact, some of this data is actually extremely tailor-made so that this graph could be made possible. But this is something that that is generally done. Another application for this is actually in genetic sequencing of large populations like in India, in America, and so on, where we actually look at specific things that is found in the genetic chromosomal sequences of this gene of these people, so that we can say, okay, these people have this ancestry, these people have this ancestry, and so on. That's also actually done by clustering. Now we can move on to the next slide. Thank you. Now we come to the next, the last type of data analysis, which is known as confirmatory data analysis. In general, this goes by a lot of names, but it is also very popularly called as statistical hypothesis testing. What we do is that we actually test between two sets of data. We start from a position of that these two data sets don't have any relationship between them. That's always the default position that we generally start off with, and we call it the null hypothesis. However, even when we do this, it is very important that we check our assumptions, because if our assumptions are based on pre-existing faulty data, the hypothesis that we use for checking this is already going to be biased, which means we are just now dealing with bad data, bad hypothesis, which means that our conclusions themselves, however statistically significant they are, will have no merit altogether. Once all of this is done, we have performed all the checks that we have. There is one thing that we can actually always see that we use in general is known as the test of significance, which is known as p-testing. Essentially p-testing, I think we will all be familiar with the whole normal distribution in general. So p-testing is in general the probability that some event occurs with a greater probability than this, which means that if you're starting from a null hypothesis, the data that we collected falling in due to that null hypothesis itself is either statistically significant or statistically insignificant. We generally have a threshold for that. If the data falls beyond the threshold, then the null hypothesis is rejected, and we know that there is a significant correlation between this data. Otherwise, the null hypothesis is accepted, and this data sets just don't have any correlation. Can you move to the next slide, please? Yes, thank you. I have just presented an example, and this is a very recent study. Whenever we do science, we actually move it for peer review in general. There is actually a very well-known meme about the reviewer tool always being very difficult to deal with and be more obstinate in general. So these people actually made a study to examine whether this is actually true, whether reviewer 2 is actually worse than reviewer 1 in terms of evaluation. What these people actually found that it's not actually reviewer 2 who does it, it's actually reviewer 3. However, in fact, reviewer 2 does not have a lot of significant deviation from how the data analysis, from how reviewer 1 actually makes the review in general. So why is they actually also wanted to test why exactly is it that reviewer 3 is so grumpy in general, and they actually hypothesized that maybe when the editor is sending away mails for reviewers to check, the person who accepted last is actually either going to be very busy or going to be actually a person who doesn't really have a lot of time. So which means that the reviews are going to be a bit biased in a sense. So that's why reviewer 3 is going to be a very difficult reviewer to deal with sometimes in general. If you move to the next slide, it shows the it shows the whole data sets that they analyzed for reviewer between reviewer 2, 3, 4, and 5 in comparison to reviewer 1. As you can already see, all these data sets report the p that they use. They take a p-value of less than 0.05 with a sample size of around 3,400, which is actually a very fairly large sample size. We can move to the next slide, essentially. Thank you. Once now that we have actually already done this, it's actually, I just wanted to tell you of what exactly that we use to do all this data analysis in general. There are a lot of software actually here. Python is one of the most prominently used data analysis softwares at the moment. However, R and MATLAB also are really very good examples in general. SQL is a database management system, so if you're working with a lot of data, you generally have to know SQL in general. The rest of SAS and Java are generally used by a lot of different companies depending on how they make their systems. Python is very accessible. Python is very easy to learn. So if you ask me, or if you ask me for a recommendation on starting off with something, it's Python. That's definitely something that you would want to learn at this moment. Can you move to the next slide? Thank you. Once we have actually developed an intuition on data analysis, it's fairly easy to see that other data analysis can be done by machines. We can actually tailor-make our machines, tailor-make our algorithms to do data analysis for us. It does not mean that it's actually for the best. There are always problems there, since all these algorithms have made themselves by the humans, and sometimes data collection itself can be very biased. So beware of these problems. Let's move on to the next slide and look at some of these problems. Yes, one very significant thing is that correlation into datasets does not imply causation between them. There was a very significant study sometime that came up around 10 years ago that cell phone towers can cause cancer and so on. And this comic essentially was made at that time as a response, where they actually inverted which data sets they were comparing. So total cancer incidence and cell phone users essentially went up at some point of time. So the correlation that the causation that you can ultimately derive from is that as cancer went up, cell phone users, like cancer causes cell phone, which is obviously one of the most bogus claims that you can make. These are some of the claims that you can make if you don't actually strongly see how correlation does not imply causation. So even if you have a correlation, try to test your hypothesis on a different data set, see if it's significant, and try to find a natural explanation to substantiate it in general. So that now, once you complete the trifecta, you have a good scientific hypothesis to back your data. A lot of times this is not done. Can we move to the next slide, please? Yes, this is one slide of two in general, which shows the various ways in which we generally make mistakes while we are analyzing data. One of the most prominent is cherry picking, where we actually choose the data that we want in order to have the conclusion that we find. The next is data dredging. Again, as I said, if you are finding some hypothesis based on patterns from such data, do not test that hypothesis on the same set of data. It will be biased. It will give you statistical significance on the same data set. However, that's not true. Just use a different data set to test whether it's actually true or not. Survivorship bias, essentially, sometimes a lot of researchers have a very strict threshold in how they collect data. Sometimes the threshold is very strict. And the reason that since our threshold is very strict, it means that only the most statistically significant data is what we are seeing. That's not always true. And you have to justify why your threshold is very strict. That's one of the first things that you must do whenever you're working on data analysis. Another thing is co-private, where you're actually collecting data from a lot of people. However, the reward that you give them in order to collect the data is actually bad. So if you ask someone to give their name and you're giving them an electric shock, it makes them less susceptible to actually saying their name again to you. This is not how you collect data. Collect data using a way in which the other person is also comfortable. False causality, as we already said, something that from the correlation, this should not imply causation. Gerrymandering is something where we just divide the data sets in a way so as to imply our collisions. It's not exactly cherry picking. As we are not collecting data, we are just subdividing it into different ways. The rest three are sampling bias, Gambler fallacy, and Hawthorne effect, are essentially related to probability and how we actually confuse probability with our day-to-day life and so on. If you move to the next slide, thank you. Yes, these are also some of the other fallacies that we can fall down, that we can easily fall into. So I would really ask you to actually know about these fallacies, and whenever you're doing data analysis, to actually see that, okay, this is not what I am falling into. I need to be a good data analyst. I need to actually understand that not everything that is published, or not every model that shows a correlation or a causation is going to be statistically significant or is going to be correct. Sometimes correlations just occur due to chances, and we have to understand how do we actually know how do we know if it occurred by chance or not. With that said, let's just move to another aspect of data analysis that we see in the next slide, the ethical concerns with data analysis in general. As I said, we have a huge data in general, data set in general for us to tinker with, to analyze in general. But in general, we must also ask, where and how was this data collected? Are we using the data from people who actually consented to share this data? Or was this consented illegally, or was leaked from some point? Is it then even good to analyze this data? Because it will say something about someone which that someone is not actually going to tell you by themselves. Is it something that we want to do? And it's always good to know that if such data exists, is there a way to protect our data from not being used by people who do not have our best interest in mind? In today's world, a lot of data is available throughout the internet. So, and people who do not really, who really should not have access to this data, actually have access to this data and can learn a lot about us in general. In that case, it becomes very difficult to us, because then we can become the target of propaganda by a foreign country, by a person who does not have the best interest in mind, and so on. Not only that, the data can essentially be tinkered with, which means that the data analysis that we do is from fake data. So anything that we do based on this fake data is completely spurious, and it cannot be relied with. But if we don't know that it's fake, don't know that it is from fake data, we are not going to be. We are only going to fall deeper into the pit and become more and more, well, let's say polarized in general. If you move to the next slide, I just want to show from this graphic as how this polarization has actually already happened in US in general. If we see from 1994, the median Democrat and median Republican were actually very close together. But since then, they have actually moved apart, and this has been very fast from 2011. Much of it has been attributed to the rise of misinformation, from the rise of propaganda, and the rise of echo chambers, in which people have analyzed data that all these people have provided in ways that they did not want, and have targeted them in order so to create enmity between these two groups of people. It's essentially important to understand that we share this world with a lot of people who can essentially be good. It's not always good to fall prey to propaganda, which tells us that these people are bad, or these people want to destroy us or something, and recognize this so that we are not polarized in the same way as the US people have now been polarized. With that said, I'll now give various examples of data sets of bad data visualizations that we generally use in data analysis, and the faulty conclusions one can generally use when we see them, and see why it is very important to do good data analysis in general in today's world. Can we move to the next slide? Yes, one very important thing that a lot of different people do is that when they look at the global temperature data in order to assess whether the temperature has changed, whether the temperature has increased over a period of time, is that they look at this data and then plot trends. Now, in general, your trends should be plotted over a large amount of data. These two red lines are significant. However, a lot of people generally take only a very small sample of this data, these blue lines, and then think that, hey, the temperature is not changing. We are just thinking about something which is not happening. Maybe they're deluding us. Maybe they're trying to tell that this is a conspiracy and so on. It's very important to notice that, to note that all this data is available in the public. You can actually do this. You can see it for yourself. Yes, temperature change is real in general. So beware of all these false things that people can spread. Can we move to the next slide? Yes. Another thing that we actually notice in today's world is that a random gamut of medical or health news coming up that something can cause something in some population. Now, it's always significant. Sometimes this is so frustrating, is that one newspaper in a particular on one day can publish that coffee can cause heart attacks in males above 40 years of age, and 2 days from then it will publish another news report saying the effect of coffee on heart attacks is actually not statistically significant. So which news do we believe out of this two in general? It's actually easier to understand all these news if we actually understand how the studies are being done. A lot of the studies don't actually do this clinical trials. They actually look at data sets, try to find a correlation between those two data sets, and just publish it. This is known as, essentially, this is actually also an example of data dredging, where they actually don't do the clinical trials, they actually don't do it practically, they just find it from data and then publish it. Yes, it is statistically significant, but when you do the clinical trial, none of this matters because it's essentially not going to work. So I would say beware of such news in general. See how this data was collected, see how they analyzed this data, and see how they came to the conclusion. Oftentimes, these data sets are very narrow, and they only apply to a very specific subset. If you don't fall into that subset, don't worry. You are not really at risk or not at risk or so on. Can we move to the next slide? Yeah. This is also another thing where people very commonly misuse the pie chart. Designers often think that a pie chart is something that looks beautiful, but a pie chart is something that in general, it should be informative. As this pie chart shows, it adds up to 193% instead of 100%, which is bad. You should not do this. And whenever you do this, essentially you should tell them, okay, you're doing bad. This is a bad data analysis. It gives us a false conclusion. 60%, 63%, and 70% essentially may have equal proportions, but they do not add up to 100%. And this tells us nothing about the whole vote share, about the people that they analyze the data from, and so on. Can we move to the next slide? Yes. This is also another way to completely botch data visualization, leading to false analysis. So if you see the y-axis, it does not start from 0. It just starts off from an arbitrary unit and then goes up from 5 foot to 5'7", which means that whenever someone designs height based on this, it means that people who have 5 feet height often just are so small that it does not even reflect the real data. This is bad. This does not accurately depict reality. So please stay away from creating such visualizations in general. Can we move to the next slide? Yeah. This is also another slide which we generally don't know if it is propaganda or not, but it's not really untrue. Yes. One thing you must note is the inverted y-axis scale which is used here, which in general should be avoided. Your y-axis must always increase when we go up. It should not increase when we go down. Here, since we are using an inverted axis, it means that we actually can make some false conclusion if we don't see the axis. Just from the data trend, we think that, okay, the crime rate is going, the gun death is going up, and after some hours passed, it is going down. However, the trend is actually opposite, since the axes are inverted. Not only that, the use of RAID as a data visualization technique essentially for above it means that it actually already prejudices your conclusions in general to what you are trying to think of this data. So whenever you are looking at some data in some sense, when you are trying to analyze it, please look at it very well. Try to see if they're trying to mislead you, try to see if there's something wrong in that, and then make something of your own. Can we move to the next slide? Yes. This is another way in which we misuse pie charts in general. None of these category, none of this batsmen or none of these percentages of runs should actually be in a pie chart. All these people belong to different cricket teams, that and their percentages do not even add up to 100 again. And there is no possible reasons why they should add up to 100. Then why do I even use this chart? Is it good for analysis? Absolutely not. If it is not good for analysis, do not use such charts. It's very important to stay away from charts in general. Can you move to the next slide in general? Yes, this is also another way in which data dredging or data mining occurs, where people just take two unrelated data sets and then try to compare them and try to think, okay, since the trend actually increased after it fell for Netflix back in 2013, Tesla is somehow always following the same pattern. It's falling down, and maybe we'll bet on it increasing at some point of time. This is not how you do it. This is a very bad correlation, and there is no possible reason why it should even happen. This is bad data analysis in general. Can we move to the next slide? Yes, this is also another way in which people generally try to do a propaganda in which they try to say, okay, something is increasing, something is decreasing, and then do not show the y-axis at all. This is bad, and the correct way to depict it is in the next slide. Can you move to that? Yes. If you can see now, the one they were trying to say were actually increasing is actually staying mostly constant over the years, even though the other one is still considerably decreasing. So the other picture was very misleading, as you can always already say. It can lead to a very different visualization, and in that example was actually used by a lawmaker to present to present their point. That should not be the case. Even if you are trying to justify something, always use good data analysis. And with that said, I think we have come to the end of our lecture. I hope that you had a very nice time understanding what data analysis was and could develop an intuition about how to analyze data, how to visualize it, how to couple it to what we see around us, and so on. I hope that you use it to actually interact with the world around you, to interact with a lot of data that we see around you from newspapers, from the stuff that you actually read, from stuff as you hear, and so on, and then use it to be better human beings and good data scientists in general. Thank you very much.
Thank you, Mr. Spandan Das, for your presentation on data analysis. Now I am requesting our principal madam, Dr. Mrs. Deepali Soren madam, to kindly say a few words.
So nicely, he has explained all the matters, like regarding the data mining and how to do the clusters based on the similar data. I think that students has got that idea, and it will be help them to think in the new direction of the data mining, or you can say data analysis. Thank you once again. Thank you to all.
Okay. Thank you, Mr. Spandan Das. We will go ahead and take some questions. So just a reminder, please be sure to type your question into the question box in your control panel. So it looks like we have very few questions. So first question is, which one is most difficult, whether data mining or data analysis?
That's a very good question, but it's also a question that can be answered in this way. Data mining is essential to data analysis in this day and age, which means that you cannot do data analysis just for the sake of doing data analysis at some point of time. Of course, data analysis is more intuitive. Data mining means that you must learn some algorithms in general and must learn some programming language. So in that sense, data mining is more difficult in a way. However, since both of them are really tangled so much that you can do one without you doing the other, it essentially means that data analysis has to build upon data mining, so both are equally important.
Thank you, sir, for explaining the topic very nicely. At the end, thank you everyone. We appreciate you for being here. We uploaded the feedback form at your registered mail ID and also on the chat box that is at YouTube streaming. So please submit the feedback form in order to generate the certificate of participation. It is an announcement that on 16th July 2020, we are organizing our next webinar on power system. So keep subscribing to our channel for latest events. Thank you again for joining with us today, and we'll see you next time. Have a good day. Thank you.
Thank you.
Thank you, sir.